Hello friends, welcome back to my YouTube channel. I am Deepak Joshi. This is my first tutorial on quantum physics. In this tutorial I have introduced and explained every theories in much simple way. I hope everyone love this video. How your classical physics is different from quantum physics. Is the knowledge of classical physics enough sufficient to deal with real physics? The concept of classical physics is not only sufficient to understand the universe. Classical physics will approach you to the topic surfacely. So to study the same physics at atomic scale, the concept of quantum mechanics is most needed. This physics is almost hypothetical, and we are not having so much clear evidences to make sure that every theoretical concepts really exist in nature. Even mathematically the experiment comes true, it doesn't mean necessarily that derivation is true. Today in this tutorial I will present the short history of quantum physics. How it comes into dominant. How it is expanding its concept hypothetically. Let's begin. Quantum mechanics, a mathematical model of science dealing with the behavior of particles at a subatomic level, is the most fascinating area of physics in last century. Advancements in quantum mechanics were only made when humans started to observe physics beyond the visible eye, beyond the macroscopic universe. It is where the absolute laws of classical mechanics failed and a new probabilistic model arose. This all begins from Newton's. When Newton studied the light, he said that light is a particle, and wrote his corpuscular theory stating particle nature of light and supporting ray optics. But this theory failed because it couldn't explain all the phenomenon of light. After Newton's, Huygens started to study light, and he said that light travels in the form of wavelets, that is, light is a wave, and he proposed his wave theory, commonly known as Huygens wave theory. The Huygens theory would supposed to be failure if Maxwell's had not supported him. This is because Huygens theory was only limited paper but not experimentally verified one. He kept on performing his experiments continuously, but he couldn't till his death. The electromagnetic wave theory of Maxwell's supported Huygens theory. Later in 1920 the student of Huygens started to give continuity to Huygens' theory of wave nature of light, and finally he proved wave nature of light experimentally through his double-slits experiment. This experiment today we read as Young's double-slit experiment. In his experiment particles were shot between two different slits to end up on the wall on the other side. The result on the other side completely denied our intuition, as particles behaved like pebbles being thrown at a pond. It started to behave like a wave, and it started intersecting with each other, creating a weird pattern on the other side. Instead of creating just two different strips of dense particles on the screen, it created an interference pattern alternating between dense and empty screen. This confirms the dual nature of particle. If you look at the particle, then only it will behave as a particle, for this detector was used just similar to CCTV. And if you do not look at the particle, the same particle starts to show its wave nature. It means in your practical life you will only see the object if you are curious to see, else the same object may have traveled somewhere other. For more simplicity, the table in your room will not be in your room if you go out of your room. At this time no one is detecting at the table, so at this period your table might be behaving like a wave. But as soon as you enter into your room the table appears exactly at the same position. This seems somewhere magical, but this is what's happening with us. They repeated the same experiment with different variables. An important version of this experiment involved single particles. Sending particles through a double-slit apparatus one at a time resulted in single particles appearing on the screen, as expected. Remarkably, however, the same interference pattern emerged when these particles are allowed to build up one by one each and every time. But how can particle be at all different places at the same time? This is where Schrodinger formed his famous thought experiment. Imagine a cat in a box with a radioactive element. It has a 50-50 chance of surviving in 1 hour. Now, to the observers outside the box, the cat is both dead and alive. Even after 1 hour, our knowledge of the cat's condition would be dependent on whether we opened the box or not. So in a way, it's our curiosity that might kill the cat, not the radioactive element. Now, This paradox being a reality can seem really absurd to people including me, but this essentially is the Copenhagen doctrine. This interpretation was devised in years 1925 to 1927 by Niels Bohr and Werner Heisenberg. According to this interpretation, these physical systems, consisting subatomic particles, have no definite properties prior to measurement and the collapse of the wave function. It concludes that quantum mechanics can only measure probability of the particle trajectories through a physical apparatus, but cannot determine with certainty. Incompleteness is one of its core features. As the wave function collapses, it succumbs to nature as if there is no certainty. Einstein completely opposed this set of ideas as he published his EPR paradox paper in 1935. Going back to the Schrödinger's cat experiment, a cat can be in only two different states in the box, dead or alive. These are two entangled actions that are dependent on each other. It turns out that these dependent actions can be found in particles too. These entangled particles form in the same point and instant in space. They have such a deep bond, they share the same wave function. They can be placed infinitely apart, spanning from one galaxy to the other, but measuring one particle will instantly influence the other. Einstein famously called it spooky action at a distance, and also had this famous remark on quantum mechanics: God does not play dice. He concluded in his paper with his colleagues, then either the description of reality given by the wave function in quantum mechanics is not complete, or may these two quantities cannot have simultaneous reality. Niels Bohr had personal debates with Einstein over the state of quantum mechanics. Einstein rejected the indeterminism of quantum mechanics that Copenhagen interpretation offers, but Bohr concluded that quantum mechanics is complete and nothing else would be needed. This divisiveness is not only between these two individuals, it's the same between the entire scientific community. A survey done among mathematicians, physicists, philosophers on their favorite interpretation of quantum mechanics, 42% choose Copenhagen interpretation. Science is about being sure of something, and it's surprising to see less than half of a scientific community supporting something that conventionally taught as quantum mechanics now. Quantum mechanics has been around since the 1920s and still it divides opinions, further convincing us to explore more than to adopt Copenhagen doctrine. So how do we explore more then? Going back to Einstein, he was the leading proponent of what's now called hidden variable theories. According to him and some scientists, the theoretical foundation of Copenhagen interpretation lacked the consideration of all the variables present in a given state of a physical system. Hidden variable theories conclude that there are hidden variables that affect the state of measurement in a quantum scale, thus affecting the outcome, making it seem random. Now to understand this in generic terms, let's consider a fair coin. If I flip a coin, there is no certain, deterministic answer to what the outcome would be, so we express it as a probability of two different outcomes in a fraction. But in theory, if I know the coin's initial position, initial state of heads or tails, and the forces surrounding that object, how hard the surface is, I can completely predict the outcome. So a fundamental action, which might seem random at first, turns out to be not so random after all. Just substitute the coins with particles and the forces surrounding that object with velocity vectors and you get Bohemian mechanics or pilot wave theory. Pilot wave theory uses Schrödinger's guiding equation instead of wave function to give a more deterministic result towards the end position of the vector. It gives valid results for dual-slit experiment but falls short when it comes to relativistic particles. It's still quite popular among some scientists for successfully describing something as quirky as the dual-slit experiment. Copenhagen interpretation survives for now for being the most experimentally useful and accurate. But it doesn't provide the answer to questions like why or how. There hasn't been much theoretical development in quantum mechanics recently as we are still struggling to prove the previous theories. However, uncertainty only means our inability to process information, and it's the job of scientists to not only apply scientific phenomenons but also to understand them. So, pursuing a complete physical description of subatomic particles needs something beyond than Copenhagen interpretation. It because cannot be considered completely. You set up your apparatus in a particular configuration, you can measure the outcome of any such experiment you perform. What happens if you force the interaction between a photon and the electron as it passes through the slit, but never record the information? What happens if you don't look at the information you do record, but look at the screen before you ever look at the information? If you then go and destroy the information and look at the screen again, does anything change? Each experimental setup will give you a unique set of results, and each result you get provides you with little piece of information about the quantum picture of our universe. If you want to know what reality is, it's this: what we can observe, measure, and predict about nature under every combination we can dream of setting up. To learn more, we have to look to experiments and observations. Those results, rather than which quantum interpretation you accept, show us what's truly real. Hope you get something interesting facts hidden to you in much simple explanations and examples. If you like the video, hit the like button, and if you want to get informed periodically, don't forget to subscribe my channel. Follow me on Instagram at deepakjoshi252 for more information.